Hello, I'm Carl Nelson, and I'll present design of a modular, cost-effective robot arm for increased dexterity in laparoscopic surgery, which is a project that we carried out at the University of Nebraska, Lincoln last year. The problem that we're addressing has to do with surgical robotics. Commercially available robots tend to be these large things with fixed kinematic configuration, usually a long, rigid, straight shaft with some concentrated dexterity or degrees of freedom like wristed motion at the end of the instrument. And what we're interested in is developing small, disposable, modular type robots that have their degrees of freedom distributed along their length, so they have different kinematics than the existing robots. And we believe that this could facilitate different types of surgery where there may be obstacles to straight line surgical site access. We're also interested in reducing cost and reducing the size of these robots by limiting the number of cables required to actuate them. So we actually introduce elastic antagonists whereby we can actuate a joint with one cable and the return force, if you will, from that degree of freedom, that joint, is provided by a spring. So we can make the robot more compact because it has to enclose fewer cables. And on the lower right, you can see what we had done in previous work, but what we're interested in now is making this more modular and improving the cable routing and some of the force transmission characteristics. So here's what we designed. This is a 4 degree of freedom robot, 3 rotational degrees of freedom plus 1 grasper, and each of these degrees of freedom is driven by a single cable with an elastic antagonist. In the grasper, it's just a little torsion spring here, and in the other joints, it's a coil extension spring that's housed inside the link body. And so this allows us to use space efficiently. We also built a lever-based test bench, which allows us to easily visualize how the robot's working without hooking up all electronics and actually driving the tension of the cables through motors. And we did some simulation using MATLAB to visualize the workspace that could be produced by modularizing the link lengths and the joint orientations with respect to the links. So this is what you'll see at the lower left, is a couple of the results of these workspace simulations. We would like to work further on this to turn this into a design tool that would allow a clinician to assemble a robot that performs well for a particular type of operation based on its kinematics and kinematic properties. On the upper right, you can see the prototype that we developed with the lever-based test bench. So by moving these levers, you actually move the robot around, and you can see that the little aluminum sections are the links, and the little black sections are the joint modules. You can see that these 3 joint sections are identical, so they're modular. The links themselves can be interchanged or replaceable with links of different shape and size, and that's essentially what we were simulating in the workspace simulations. Improvements in this design compared to our previous work: we now contain all of the cables within the body of the robot. Everything is routed inside. You don't see any loose cables sticking out. So that's nice and clean. We're still able to reduce the size compared to the previous iteration. We improved the cable routing through the joints. So now we have little cheap pulleys that we use, and that improves the friction properties, and it also allows us to improve the force transmission properties because now we have nice constant moment arms, so our force transmission is very uniform. As I mentioned, the robot is now also reconfigurable because of the modular link design and the modular joint that is identical across all the different Revolute joints. The use of the metal springs that are aligned down the link body actually allow us to improve our force transmission capabilities in the robot, and also get around the issues that we had with performance degradation over time with elastomeric antagonists. And we're interested in taking your questions and having your comments, so maybe you'll reach out to us. Thanks for listening.